In this video, we're going to talk about the central limit theorem, which is one of the most important theorems that we use throughout statistics. And so I want to kind of give you a broad overview of this particular theorem. Typically, when you're doing real world statistical research, we often sample several individuals, not just one. Up to this point, we've been considering what happens if we select one individual or one subject. But guys, that's very impractical when you're doing true statistical research. And in most cases, you're going to be sampling several individuals, ideally 30 or more. And so when we sample those several individuals, okay, we gather together those several individuals. Remember, that's called our sample. We're going to compute or calculate the descriptive statistics for that sample. Most importantly, we calculate the sample mean and the sample standard deviation. We use those two descriptive statistics because both of them involve all of the data values. So we're taking into consideration all of the data values. The challenge becomes that as we take different samples from the same population, we will likely get different values of the sample mean, and probably also different values for the sample standard deviation. So ultimately, what happens when you're looking at a group of values instead of just one is the sample mean becomes a random variable because it could have different values depending upon your sample. And so because it becomes a random variable, we can then assign a particular probability to the probability that we would have that particular mean for a particular sample. So the probability distribution of the sample mean is called, in statistical terms, the sampling distribution of the mean, which is X bar. Okay, so the probability distribution, which we've been talking about recently in the lessons prior to this, of the sample mean is called the sampling distribution of the mean. Why do we care? Why are we so concerned about the means? Well, remember, the means are a measure of center. And so it gives us a way to begin to compare the different samples or the different groups. So, and again, remember, it includes all of the data values. And so that's important. That's why we focus on the means. And again, the means are reasonably easy to calculate. I mean, if you had to do it by hand, you just simply add them all up and divide by the total number that you have. But we also have calculators, computers. Even nowadays, a cell phone could do it for you. So they're very easy to calculate. The central limit theorem is one of the most powerful and useful ideas in all of statistics. Okay, and again, it's related to this idea of using several individuals or a group of individuals as opposed to a single individual when we conduct research. And so I want us to explore together the characteristics of the central limit theorem, because knowing that the data is going to behave in a predictable way is going to be very useful to us. Okay, so we're going to explore the characteristics of the central limit theorem together. And we're going to do that using an example. We all, or most of us, have a Social Security number. And I want us to focus specifically on the last 4 digits. You may not know and you may not care, but for your Social Security number, the first 3 digits are tied to your state of birth. The next 2 digits, which are in the middle, they're considered a group number that is sequentially issued during a particular period of time. And then the last 4 digits of your Social Security number are supposed to be randomly assigned. But the question is, are they really? And so we're going to take a look at that. So here's the setup. The question is, are the last 4 digits of your Social Security number truly random? So years ago, before we went to using student ID numbers, I had access to Social Security numbers. And so I determined the last 4 digits of Social Security numbers for the students that I was teaching at that particular time. And I sampled 131 people, or 131 students. And so from each one, I collected 4 numbers, the last 4 digits of their social. So I have a sample size of 524. And we're going to look at those 524 individual data values. It says this, if I have 524 different data values. And let's look and see what happens. Here's part of this. Here on the left, you see part of the spreadsheet. And I put them in columns 0178, 5040, 1274. Those are the last 4 digits of Social Security numbers for anonymous people. Okay. And then I took all 524 of those and I created a histogram. Okay. Or actually, this is a bar chart. It's not really a histogram. But notice that the shape of this histogram is approximately uniform. If you'll remember, and I'll kind of draw it in there for you, remember early on when we talked about the different distributions, one of them that we talked about was uniform, where that basically it looks like a rectangle. And for the most part, this particular graph does look like a rectangle, which implies that each digit occurs approximately the same number of times, which would lead me to surmise that it is random or uniform. If we average together those 524 individual values, we get a mean of 4.45229 and a standard deviation of 2.897156. So we start out, here's kind of the neat thing, we start out with a distribution that is not necessarily normal. It's not that bell-shaped curve that we love so much. Okay, we actually have a uniform distribution. Okay, so then the second thing that I did is I looked at each one of these sets of 4 as a group. Okay, so I took this first group, 0176, and that became a group. Okay, and I found the average for that group. So I added these numbers up. 0 plus 1 is 1, plus 7 is 8, plus 6 is 14, and then I divided by 4. And so I get this list, okay? So if we look at each person's last 4 digits as a group, I had 131 groups of size 4. And again, I took each one and found the average. So for the second row here, 5040, I would have added those, gotten 9, divided by 4, and had an average of 2.25. Again, if you want to skip down and look at row 20, for example, I had 3, 7, 8, 1. So 3 plus 7 is 10, plus 8 is 18, plus 1 is 19, divided by 4. Okay, so hopefully you get the idea there. Okay, so we looked at each row as a group of 4 and found the mean or the average for the group. So then I created a histogram of those averages. Okay, so this histogram here is the histogram for this column F on my spreadsheet. Notice how the shape of the histogram is not uniform anymore. It almost has, and again, let me kind of see if I can help by drawing it in for you. It almost has that normal, it comes to a single peak and then it begins to taper off. So now we went from having a uniform distribution to a normal distribution when we considered those last four digits as a group. Notice, and I'm going to show this to you on the next slide in just a minute, that the mean for those values is still 4.45229, but the standard deviation has actually gone down. It is now 1.475803. Let me put those numbers side by side so you can see. When we looked at the individual digit, we got a mean value of 4.4529. Even when we looked at the group, okay, at the sampling distribution, we got the same mean. So notice that the mean for the individual, okay, the mean for the individual is equal to the mean of the group. And the way we show that it's a group, we put a little X bar as a subscript. Okay, so, and I've proved it to you because I've used an example, and you can see the two numbers are the same. The numbers that are different are the standard deviation. Notice that the standard deviation of our group is lower. And guys, I kind of hope that makes sense to you. Think about it. How different would one individual be from everybody else? Guys, one person could be really different from everybody else. Whereas if you're looking at, 10 people or 20 people or 30 people, or in this case, 131 people, they're maybe not as different. They're closer to being, kind of normal or average, more like everybody else. So when you think about the group would tend to vary less. Okay, so, and the numbers show that basically in this particular case, because the standard deviation is smaller, that it varies less. And so when you start thinking about a group varies less than if I'm just looking at an individual. And there's a very special relationship that exists here. You have the original standard deviation, and it's actually equal to the original standard deviation divided by the square root of your sample size. So this particular data value, this value for your standard deviation here, should be approximately the original standard deviation, 2.897156, divided by the square root of the 131 groups that I had. Okay, and I can prove that to you. Let me see if I can get my calculator pulled up where you guys can see it, and I can really prove that to you. You don't think I'm just telling you a story. Takes just a minute to come up. Okay, so there's really three things that are going to come out of the central limit theorem. Okay, but here's my calculator, so let me prove this to you. Okay, so we had two. Let's see. We had two. I can't get to it. Hold on. Point. Eight. 2.897 156 divided by the square root of the 131 that were in our initial sample. Okay. Oh, I'm sorry. It's my fault. The N was the group size. Okay, so it should be 4. I'm sorry, I made a mistake. 2.897156, and I'll correct it in just a minute. Divided by the square root of 4, because we had 4 in each group, our group size. Okay, and I get 1.448. Okay, so if we go back and look, and Miss Ralston corrects her mistake, sorry about that. My fault. Okay, so this should be by my group size, which was 4. I get 1.44. So estimation, this would be 1.44. So I am, a little bit off, but again, there is that relationship there. And again, I made a slight mistake. Okay, so, but here's the 3 things that really come out of the central limit theorem. One is the sampling distribution of X bar is approximately normal. So regardless of what type distribution you start with, if you have a large sample, which is 30 or more, and you apply the central limit theorem to that distribution, then it becomes approximately normal. And again, we saw that because we went from a uniform distribution to virtually one that was symmetric or normal. So that's the first thing, is that any distribution, if you have a large sample and apply the central limit theorem, will become approximately normal. The mean of the sampling distribution will be the same as the original mean. And again, I just proved that to you here. We saw the numbers. The mean of the original is equal to the mean of the sampling distribution. And then finally, the standard deviation of the sample means will be smaller than the standard deviation of the population. It will be equal to the population standard deviation divided by the square root of the sample size. It's not really the square root of the sample size, but it's the square root of the group size. Okay, did you have a group of 4, or did you have a group of 6, a group of 10? How many did you have? And so those are the 3 important characteristics that you want to kind of get from the central limit theorem, and realize that you need to apply those, or that they're being applied behind the scenes when you're looking at a group instead of an individual. Okay, when you look at it and you're applying it to a group rather than an individual, you'll have these 3 important characteristics of the central limit theorem. That if you have a large sample for any type distribution, and a large sample is anything greater than 30, and apply the central limit theorem, your sampling distribution of X bar will be approximately normal. The mean of the sampling distribution will be equal to the mean of the original population, and the standard deviation is smaller, and it's smaller if we take the original standard deviation and divide it by the square root of n, and n is our group size.